Law of Universal Gravitation. Go ahead and take that. Cut out every box. Cut out the border. Cut out every box. I actually have a title here. If you want to, you can glue that in. If you prefer written rather, you should prefer the typing rather than handwriting. I don't particularly like my handwriting, so I'm going to cover it up. Okay, so Law of Universal Gravitation. So this is Sir Isaac Newton was really essential for a lot of things for modern science. He really took us from very elementary science into moving into like some really quality science. And one of his, apart from the three laws of motion and from calculus, he gave us the law of universal gravitation. And this provides a mathematical explanation and description of the motion of the planets. Okay? So this applies mostly to planets and very, very, very large things, but it does technically apply to everything. So the law of universal gravitation states that all objects with mass have gravity. So even you have mass, you gravitationally create a force that attracts other objects with mass. Okay? Now, this force is ridiculously weak unless it's something extremely large mass, like a planet. Okay? But it's still something I want you guys to understand. Okay? So, there are two factors that determine the magnitude or the strength of that force. It's the force between two objects. We measure it as the force between two objects. The mass of the objects and the distance those objects have apart from each other. So let's first talk about the mass of the objects. Okay? The greater the mass of the objects, the greater the force of gravity. Okay? Go ahead and glue that in on the left. So, talking about mass. So mass of the objects and the force of gravity are proportional. That means that the bigger the mass, the greater the force of gravitational pull it will have on other objects. The smaller the mass, the less gravitational force it will have on other objects. So that proportional thing. Big mass, big gravitational force. Small mass, small gravitational force. So, looking at a few examples here. Find this piece of paper. Okay. Photocopy didn't quite turn out the way it was supposed to, but you can kind of draw that in. So, the effect of mass on the force of gravity. All right, don't glue it in yet. Let's just discuss it first. So we have two objects of similar mass. We're going to make this easy so we don't deal with numbers, fight off with numbers. Let's say they have the same mass, 1 kilogram. The force between those, if we were to once we use the formula, it's such a ridiculously small number that it's not even measurable, really. Okay? But we're going to call that force F. Okay, that really, really small force, we're going to call it F. Now, what if, keeping the two objects the same distance apart, one of them has a mass of 1, but the other one has a mass twice that mass, a mass of 2. When that happens, we are now going to have twice the force. So, for example, if this was 1 Newton, this would now be 2 newtons of attractional force between the objects. Okay? What if they were both bigger? All right? So if they both were 2 kilograms, that same distance apart, how much force would there be? Well, it would be 4 times the force, as if they were half that mass. Okay? Now notice I'm keeping the distance the same on all of these. On this one, what if I had a mass of 1 and a mass of 3? It would be 3 times that force. Okay? Now you don't have to memorize these proportionalities. I just want to give you an idea how the mass makes a difference. Okay? I double the mass in just one of them, and I've doubled the force. Does that make sense? I double the mass of both of them. Now I have 4 times that original force. So the mass really makes a really significant difference. All right. Go ahead and glue that one in. All right, let's go over here. Let's talk about the effective distance. Glue that in. The greater the distance between the objects, the less the force of gravity. Okay, so talking about distance. And this is actually measured the distance from the center of one object to the center of the other, especially when you're dealing with large things like planets. Okay? Instead of measuring it from their surface, you measure it from the center of the object. Okay? But that distance apart and the force of gravity are inversely proportional. So, that means that if I have a very large distance between them, I'm going to have a very small force due to gravity. If I make the distance between them smaller, then I will increase the force of gravity. All right, so before we glue this in, let's discuss this paper. So the effect of distance on the force of gravity. So we've got 2 bowling balls, okay? 2 bowling balls a distance apart. There's a specific force of a gravitational attraction between them, okay? If I separate them, if I double that distance between them, okay? If I make that distance twice as great, I have now only 1/4 the gravitational force. I decrease it to only 1/4. Okay? What if I made it smaller? So if I increase the distance, I get less force. If I decrease the distance, what do you expect? More force. So if I do half that original distance, I get 4 times the force if I have half that original distance. So distance also has a significant effect on the gravitational force between 2 objects. Go ahead and glue that in. All right, now that's the concept. Right there, what we've discussed so far is the concept of universal gravitation. Now, let's work with the calculation, with the formula. So we're going to go to the oops page. So there, go over to the oops page. Don't turn the page, just on the oops page. Right? Going right at the top there. Calculating universal gravitation. Or universal gravity force. Okay. So all of those little papers that you have left, find the one that has the formula. Ooh, that's a lot of glue. Glue it in there, give yourself some space around it. All right. Start with this little piece of paper. The force of gravitational traction between two objects. Put a little glue on that.
Wait, is that the formula for both of them? For the mass and the distance?
Because there's distance and there's mass and force.
This is the formula. Those are just the factors that affect it. So if you look in this, so we talked that both mass and distance have an effect on the gravitational force between two objects. Here's the formula. Mass of object 1 and 2 and the distance between them are included in that formula. Okay? So, gravitational attraction between two objects. That's the FG, subscript G. Okay? The M1, that's the mass of object 1, or the first object. It doesn't really matter which one's the first and which one's the second, so don't worry about that. Mass of your first object. M2, mass of the second object. And in the D for distance, distance between the centers of the objects. Now notice the square there in the formula. Don't forget to square when you're using the formula. Okay? And now the uppercase G. That is a very special number. Now, we've dealt with lowercase g before. That's 9.8 meters per second squared. That's gravity that's the acceleration due to gravity on the surface of Earth. Okay? Uppercase G. That's universal gravitation constant. So this isn't just Earth. This is anywhere in the universe. Gravitational constant. So that means every time you use this formula, you're going to put in the number 6.67 times 10 to the negative 11. Every time you use this formula. Okay, so for a quick review, let's look at the units of measure for each of these. So mass of the first object, mass measured in kilograms. Mass of the second object, also going to be in kilograms. Distance between the centers of the objects, that's going to be in meters. Units for universal gravitation constant, those provided. Don't have to memorize those, not to worry. And the force of gravitational attraction between the objects, the actual question. We're talking about force, so our units are going to be newtons.